All right, 9-4. 9-4. Hope you had a chance to do 13 through 15 because I'm going to do them right now. If you haven't, pause the video and we will do it later. But let's do it right now because you're already done it. Here we go. What's the population in 1990? So 1990 to 2000, population can model the following way. P equals, oops, 29816, comma 591 people, where it's going up at 0.10128 times t. Now look at that go. That's not where t's never year since 1990. So if I put in a 0 here for problem number 13, if I put a 0 in here, remember anything that 0 is 1, so I get 29,816,591 times 1, which is just 29,816,591 peeps. Or we could look at this as, hey, isn't this just N naught, which is our initial amount? And they said initial amount in 1990, so that would be how I get that. 14, so what's the annual increase? Well, if I look at this, this is where interest or increase rate is, right? Because 1 plus R. So I go, well, R is just got to be 0.0128. Says it asks for a percent. I move the decimal point 2 points, and I go 1.28%. Annual interest rate in peeps, or people. Estimate the population this year. This year. So what would this year's population be? Well, okay, that's 14. So what do I do? So 1990 was how many years ago? Looking at my watch, 16th year, 26 years, right? So I would go for 15, I would go, all right, 29,816,591 times 1.0128 to the 26th. And so I go 1.0128 up caret 26, and I get a lovely 29,816,591 times 1.39193. So multiply those together, 29,816,591, and I get a lovely 45, sorry, that's not right. I get 41,502,475.09 peeps. Can I have a 0.09 peeps? Nope. Supreme Court has ruled that you cannot have a part of a person. So you're 41,502,475. We assume that last piece does not exist. So far, so good. All right, now if this just stopped here, we'd probably be pretty happy and we'd be smiling and we'd sing our songs of praise about interest rates. And it's kind of important to know if we're doing math, but it gets worse. Read through that next one. I'm going to pause this, start it up when everybody's read it, all the way through problem number 1. Don't try problem number 1. It's not, well, you know what? Try number 1. See the frustration. All right. So, bacteria in a petri dish do not need to wait a certain amount of time in order to compound. Instead, they, under certain circumstances, are born ready to make more bacteria. As such, they wait 0 time to make more bacteria. How does this affect our problem? Well, while I was studying bacteria, on day 1 he has 100 bacteria. He knows they grow at an hourly rate of 20%. If they compound continuously, in other words, the moment they're born, they're making the next one, how much does he have in 3 hours? So we start this problem off, and we go, well, it's just n equals n naught, 1 plus r to the t. And then we start going, well, this is no problem at all. I started with 100 bacteria. I've got 1 plus, well, what's the rate? Oh, the rate's only 20%. Oh, but how many times are going to compound it in an hour? Well, it's continuously, right? So that'd be an infinite amount of time. And then, how many times are we going to compound it in 3 hours? Well, an infinite number of times, yeah. So then we stare at this and we cry a little bit. And we hope for the best because that's not good. Because if I think about this really hard, I'm dividing a really small number by infinity. When you divide a really small number by infinity, you get virtually zero. You get closer and closer to zero, so it doesn't even matter. But no matter how close it is to zero, if I multiply it by an infinite number of times, I'm going to get a number of some sort. I mean, if this was 1.01, I did it to infinity, well, it'd give me infinity, wouldn't it? But if this is 1, it doesn't matter what this number is because 1 plus 0 is still going to give me 1, so it's just going to give me 1. Well, let's look at the two extremes for a moment. If it's true that bacteria, if this is true that this is 0, that means that the effective rate is 0, which means bacteria can't grow. And bacteria grows. On the other hand, if this wins the battle, and this is a really small number, but we're doing an infinite number of times, so what would happen in that case? We'd have an infinite amount of bacteria. So the moment you put it in a petri dish, come back 3 hours later, it's covered the world. That doesn't happen either. So it's got to be something in between. Mathematicians in the 1800s played with this at length, ad nauseum, and were really concerned by this. They eventually figured it out by basically using a fancy method of guessing and checking. They basically did the math as if they were compounding continuously and then asked the question, if I did this an infinite number of times, what number would I get? And they consistently got a rather unusual number. Okay, we're going to spend some time with that number. The number is the number E. So you replace all of this with the number E. Okay, so this is the way the new formula looks like. It looks like N equals N naught, E to the R, but notice how R just got put up there. Reason for that involves calculus, not going to explain it today. RT. This is the formula for compounding continuously. Now, we can still live with the fact that we don't know how to derive this simply because it was done by brute force initially. You remember Euler? Actually, don't remember Euler. I'm introducing Euler right now. Euler or Euler, whatever his name is, he's the one that sat down and just plunked away until he figured this out. Okay? And in figuring this out, he created a way by which we could model things that compound continuously. Now, banks don't compound continuously, although you run into problems all the time where they theoretically do, they don't. But things like bacteria certainly do. Things like that have half-lives, where the amount of material determines how much dissolves the next second, also compound continuously, right? Because the amount you have is instantly decay. So here we go. Let's make sure I've cleaned up these things. So if you look at the back, so we look at 1, and here we're going to do the problem right now. We're going to go final amount, don't know. Initial amount was 100. E, that's just E. R, 0.20. T, 3 hours. Now, one of the things that rookie errors people make is they don't multiply these together first, right? Order of operation has to do that first, so that's 0.60. Then I just go E to that. Now, to find the E to the button on your calculator, you need to find the LN button. It's almost always the same one. Casio, it's in the middle. TI, it's on the left-hand side near the bottom. And it's always second function because they like ln better. We'll explain why that is later. But right now we're going to go e to the. So you go to a second function, e to the. It already lifts it, so you don't have to raise it to a power. It knows when you're using e to the button, you want a power to follow it. So you're going to put a 0.6 in there. Then times, so I got for that 1.822, right? And so then I would get times 100. I got 182.211. We're going to assume bacteria can't be partial either. So we'll round up or round down to the nearest whole bacterium. What does compounded continuously mean? It means that the moment, from the very moment, and every instantaneous moment after that, the amount that's being added is determined by how much you already have in there, instantaneously at all times. If it was a bank, that means they're throwing money in there constantly. Because they calculate how much money is in there, they constantly throw more money in there. Good bank, right? How are we going to deal with this? Again, we're going to deal with this using this formula. When you use a new formula, again, any situation where it's constantly compounding, there's no breaks. Okay? There's no breaks. Okay, so let's try the example. Everybody try number 1. I'm going to end this video and we'll start the next one in just a moment. We'll try number 1 right now though. See how it goes. Go ahead and do number 1 and good.